In this video, we're going to look at effects of the substrate structure, nucleophile structure, and reaction conditions on the rates of SN2 reactions. And our goal here is more or less to predict and rationalize when a substitution reaction, SN2 in particular, is going to be feasible, we might say kinetically, meaning occurring in a reasonable time frame. We've already touched on thermodynamic feasibility by and large. As long as we've got a good leaving group there, and for alkyl halides we kind of have a good leaving group by default, we can make an SN2 reaction go in the forward direction thermodynamically speaking. But the kinetics is a different matter. And depending on the structure of the alkyl halide and the nucleophile and the solvent used, reactions, SN2 reactions may be relatively fast or prohibitively slow, and we'll learn how these different structural factors play into the rate of SN2 reactions in this video. This first slide focuses on the effect of the alkyl halide structure on the rate of SN2. And let's remind ourselves of the SN2 reaction mechanism. It's a single-step reaction mechanism in which nucleophile carbon bond formation via electron flow like this and carbon leaving group bond cleavage occur simultaneously in a single elementary step. In order for this to happen, the nucleophile has to approach the electrophilic carbon from the back side. And if there is steric crowding, steric hindrance to that approach on the back side of the carbon leaving group bond, this will slow the rate of SN2 substitution. And so steric bulk in the vicinity of the electrophilic carbon is going to slow the rate of SN2 substitution substantially. So tertiary alkyl halide substrates basically react at negligible rates. We see that in this table. No SN2 at all for a substrate like tert butyl bromide. Secondary alkyl halides can react in substitution, but do so at a very slow rate relative to primary substrates. And here, you really want to watch out for elimination, particularly if the nucleophile can act as a Bronsted base. We'll touch on this in more detail later, after we've talked about E2 elimination. But with secondary substrates, SN2 substitution only works if you've got a good nucleophile and bad base on your hands. On the other hand, primary substrates work quite well, and methyl halides are even better, about 2 orders of magnitude faster in rate than comparable primary substrates. So tertiary alkyl halides react at negligibly slow rates. Secondary, we want to be careful. And although primary substrates are generally great, there is one exception to this idea that primary alkyl halides react quickly in SN2 reactions, and it's neopentyl substrates. The neopentyl group is a CH2 connected to a tert butyl group. And the problem here is this tert butyl group, although it's not directly connected to the halogen, as in, for example, tert butyl bromide here, it's close enough to the electrophilic carbon that there's a ton of steric hindrance or steric shielding provided by this large tert butyl group. So the neopentyl group does not react in SN2 at all. And in fact, after we've studied elimination, it will become clear why this also does not react in E2 eliminations. Neopentyl halides are remarkably stable, kinetically stable with respect to both substitution and elimination. You can see here pretty much negligibly slow rate relative to ethyl bromide in SN2 substitution. So to summarize here, the more groups we have attached to the electrophilic carbon, the carbon linked to the halogen, the slower the SN2 reaction, with tertiary substrates not reacting at all at any useful rate. Secondary substrates can do SN2, but you want to watch out for elimination. Primary substrates are fantastic, except for neopentyl, important exception there. And methyl substrates are always awesome. Methyl bromide and methyl iodide are some of the best methylating agents in common practice. These can provide an electrophilic methyl group to a wide variety of nucleophiles, and they always react through SN2 mechanisms. As we'll see later, the SN1 reaction for these substrates does not take place. The structure of the nucleophile also has an effect on the rate of SN2 reactions. And we can correlate the rate of an SN2 reaction with what's called the nucleophilicity of the nucleophile. This is the rate at which a given species donates an electron pair to an electrophile by some standard or in some standard reaction. So we don't need to worry so much about the details. The main conceptual point here is that nucleophilicity is about rate. It's about the relative rates of different nucleophiles, and this actually will cut against some of our expectations of stability and reactivity based on thermodynamic stability factors, as we'll see at the bottom of the slide. But in many cases, nucleophilicity correlates with your expectations with respect to the strength of a nucleophile based on its stability or lack thereof. For example, anions, which have negative charge, are more nucleophilic than neutral molecules, all other things being equal. So if we look, for example, at a neutral molecule like H2O versus its conjugate base, hydroxide, where we've removed a proton and created an anion, the negatively charged hydroxide will be a better nucleophile, better electron pair donor than the neutral conjugate acid water here. And this is fairly intuitive, right? Negative charge is going to make a molecule more willing to donate electrons, and it will do so more rapidly than a comparable neutral molecule. The second point here about polarizability can cut against your expectations based on electronegativity in some cases. The idea here is that more polarizable molecules are generally more nucleophilic than less polarizable molecules, again, most other things being equal. Polarizable here refers to the ability of the electron cloud of the nucleophile to deform. The more deformable that cloud is, the faster the SN2 reaction is. This leads to some interesting situations where, for example, Sr- is a strong nucleophile. Even though sulfur is relatively electronegative, it's still a fantastic nucleophile because it's a relatively large anion. Even the halides, which we would expect to be poor nucleophiles on a stability factor basis, right? These are good leaving groups. So how can we talk about them as being good nucleophiles at the same time? Well, this is a rate thing, and in fact, the rates of nucleophilic substitution of these anions are quite high, particularly for iodide, which is very large, very polarizable. This will react very quickly in nucleophilic substitutions. It may not be thermodynamically favorable for iodide to displace some worse leaving group than I-, but it will occur at a fast rate. The reaction will reach equilibrium at a fast rate. And so in the strong nucleophile category, we have things we would expect to be great nucleophiles like C-, right, cyanide and others, but we also have O-, OH-, OR-, and even HS- and RS-, where that large polarizable sulfur makes SN2 reactions very rapid. In the SN2 reaction, there are large shifts in the position of charge, and we typically make use, in many cases, of ionic reagents. For example, we might use an ionic nucleophile like sodium cyanide or something like this, right? And with charge changing places, for example, in this reaction from the cyanide anion to the bromide anion, a polar solvent is going to facilitate the reaction by facilitating this transfer of charge, stabilizing the transition state in which charge is spread out over the whole transition state structure, and so on and so forth. Stabilizing intermolecular forces, dipole forces, that kind of thing, are going to cause the reaction to go faster. So typically, SN2 reactions are run in polar solvents. But we can subdivide polar solvents into two classes, and this distinction is very important for SN2 reactions. Polar protic solvents contain OH or NH bonds, and these are capable of hydrogen bonding, and this is key. These solvents with OH or NH bonds that can engage in hydrogen bonding are known as protic. And protic evokes this idea of a proton, a positively charged hydrogen, which is sort of there in these OH and NH bonds, which are polarized toward the more electronegative atoms. So there's partial positive charge on the OH hydrogen or the NH hydrogen, and this enables hydrogen bonding, right? Aprotic polar solvents consist of polar molecules that lack hydrogen bond donor groups, OH, NH, and so they lack the capacity to hydrogen bond. So they can engage in dipole forces, and this is important to their action in SN2 reactions, as we'll see. But because they can't hydrogen bond, this actually provides a kinetic advantage to polar aprotic solvents, and we'll see how that works on the next slide. So some examples of protic and polar aprotic solvents are shown here. Notice in all the protic solvents, we've got an OH or NH bond. We've got water, methanol, ethanol, acetic acid, ammonia, OH and NH bonds everywhere. So there's hydrogen bonding capacity here, and these are all at least weakly acidic. In the polar aprotic solvents, we don't have any OH or NH bond, but notice these are all polar molecules. These are all polar molecules, and that polarity is really important to the SN2 reaction's rate. We need to use a polar solvent to ensure that the reaction occurs at an appreciable rate. This table makes the point that SN2 reactions are much faster in polar aprotic solvents than polar protic solvents. Here we have a series of nucleophiles reacting with methyl iodide at 25 degrees Celsius in a variety of different solvents, presumably at constant concentrations, so that only the molecular structure of the solvent is changing between these different reactions. We've got a protic solvent here, methanol, and we've got an aprotic solvent here, DMF, and both solvents are polar. We can notice that for each nucleophile there is a big jump in the reaction rate in going from the protic to the aprotic solvent. It's about 2 orders of magnitude for iodide, about 4 orders of magnitude for bromide, we're up over 1 million times for chloride, and 82 million times faster in the case of a fluoride nucleophile in the polar aprotic DMF relative to the polar protic methanol. So very clearly then, polar aprotic solvents are advantageous to the rate of SN2 reactions. Now, why is this? Well, strong solvation of the nucleophile by hydrogen bonding protic solvents actually inhibits the SN2 reaction. The protic solvents, which have hydrogen bond donors, these OH and NH bonds, will engage in hydrogen bonding with these anions, F- in particular, and this inhibits their reaction with electrophiles by creating a strong and sort of almost impenetrable solvent shell that's difficult for the electrophile to penetrate to get the reaction to go, to achieve the transition state, right? With all of these hydrogen bonding alcohols, for example, around the nucleophilic anion, it's difficult for the electrophile to access that space, right? And so protic solvents actually cause a decrease in rate of SN2 reactions as a result of this kind of solvent shell. So typically, when an SN2 reaction is the goal, again, you'll see a polar protic solvent like DMF, DMSO, acetonitrile, acetone, maybe HMPA in these reactions. This slide actually shows the action of a polar aprotic solvent on a nucleophilic reagent when it's dissolved in the solvent. Here the solvent is dimethyl sulfoxide, DMSO, and we're seeing its interaction both with the cation in NaCl and the anion in NaCl. And in each case, the solvent is engaging in ion-dipole interactions with the nucleophilic reagent as opposed to hydrogen bonding. So these are weaker ion-dipole interactions in this particular case. Dipole-dipole interactions would appear if the nucleophile were neutral, but in this case, ion-dipole interactions. And these result in actually pretty good solvation of the cation, but not as good solvation of the anion, since the positive end of the solvent in this case is a little more sterically bulky than the negative oxygen end. And so the chloride is not as well solvated, certainly not as well solvated as this solvent shell that we looked at on the previous slide. This leaves it a bit more naked, quote unquote, and facilitates reaction in SN2 reactions, facilitates this reacting, right? It's easier for the electrophile to access that chloride, or it's easier for the chloride to get out and access the electrophile, if you want to think about it that way. On a reaction coordinate diagram, we can actually think about this in terms of the stability of the nucleophile based on these different solvation interactions. In a protic solvent, we have hydrogen bonding, and this stabilizes the nucleophile. These intermolecular forces are a kind of bonding in a sense, right? And so this leads to stability of the nucleophile in a protic solvent. And this creates a situation where the protic solvent reaction is slower because notice, the activation energy has gone up as a result of the stabilization of the reactant. So this reaction is slower in a protic solvent because of stabilization of the reactant. When the reactant is less stable, the reaction is all of a sudden faster. So stabilization of the reactant nucleophile here actually slows the reaction down. This is why, in an energetic sense, protic solvents are not good for the kinetics of SN2 reactions.